Welcome to another episode of our deep learning web series, Comprehensive and Intuitive Introduction to Deep Learning. In today's episode, I'll be talking about a form of recurrent neural network called LSTM, which stands for long short term memory. In the prior episodes, we have seen the limitations of a feed forward network. For example, in the prior episode, I told you that in a feed forward network, the network really does not understand the concept of a sequence. And it essentially takes each training sample and it does not consider any ordering or any relationship between the parts of that particular training sample. And I showed you in the prior episode that using a recurrent neural network, you could solve that because a recurrent neural network understands that a sentence actually is a sequence of words and it needs to understand and recognize the context that is flowing across those words to determine the meaning of that sentence. The same thing with time series data or with audio. So there is certain type of data where essentially looking at the input as a sequence matters and understanding the context flow between the individual parts of that sequence is very important. And we studied this in the prior episode, season 2, episode 3. Now, once a recurrent neural network is trained, it can distinguish between these two sentences where all the words in both the sentences are the same, just the ordering of one of the word changes from being the second word to the last word. For example, she alone finished the task is very different than she finished the task alone. And, an RNN recognizes this difference because it basically takes the sentence, breaks it up into individual words or tokens, and then it essentially starts to study the context flow across these words to determine that this sentence could mean one thing and this sentence could mean another. So we studied this in episode 3 of season 2. So one of the limitations of an RNN is that it can handle short sequences, essentially sentences that have, let's say, less than 15 words. Once the sentence starts to get longer or the time series window starts to get longer, the accuracy of an RNN starts to deteriorate. Now, in the real world, sequences are definitely much longer than 15 words. Let's take an example. Let's say that I'm trying to build a neural network that can understand the sentiment of a user review. And the product I'm reviewing here is a coffee maker. Now, the review left by the reviewer is something like this. This coffee maker dripped water all over my counter, and its drip tray warped after only a week of use. The filter basket rusted, and the fragments of metal ended up in my coffee. It also stopped midway through the brewing cycle twice in the first month. However, the brewed coffee tastes surprisingly rich, and the stainless steel finish looks sleek. Now, this review is certainly more than 15 words. I think it is about 60 words or something like that. Now, there is a pattern here. If you look at this pattern here, what we see is that the negative sentiment that is being conveyed in this review is towards the beginning of the review or beginning of the paragraph. But towards the end of the paragraph, the sentiment starts to turn positive. But the net sentiment of this entire review is that the user really did not like this product because it malfunctioned and it had issues, even though the taste of the final coffee that came out was good. The predominant sentiment here is that it is negative, correct? And we have to build a neural network that can actually understand the context that's not just towards the end of the sentence, but also at the beginning and in the middle parts of the sentence. Okay. Now, why is it that recurrent neural networks actually struggle when the sequence lengths are longer? Let's understand that first. So let's go back to building a neural network that can understand the sentiment conveyed by a review. So let's say the review is something like this. I returned the coffee maker. It malfunctioned often, though it made good coffee and looked sleek. And our task is to build a neural network that can take this text and classify it into one of these five possible sentiments. The user keeps the product, the user keeps the product and buys more, keeps the product and writes a review, or returns the product, cancels before the product is shipped, and so on. Okay, just purely based on the review left, we would like to, you know, classify the reviews into one of these five categories. Now, one might question and say, hey, why do we really need to build a neural network for this? Can't we just use keyword matching techniques to determine one of these things? It clearly says here that the user returned the word returned appears in the sentence. So most likely the classification here is number 4, returns a product. Actually, keyword based matching really doesn't work, because if, let's say, the review was, I was worried because the seller shipped a returned coffee maker, but it looks and works just like new. If you were to use a keyword based matcher, you would essentially look at the word returned and say, oh, maybe the user actually returned this product. So just based on keywords, you cannot determine the sentiment and you cannot classify. So we need a neural network that can actually understand what is being conveyed in the sentence to make the right classification. Okay. Now, with this example, let's try to understand why is it that a classical RNN struggles when the context length is much longer. Okay. So how is this actually processed? How is this sentence processed by a recurrent neural network? We studied this in the prior episode, season 2, episode 3. But just a quick recap here. So you take the sentence and you're training it. So you essentially need to know the ground truth value. So the ground truth value here is, okay, this sentence, you see something like this, it means that the user returned the product. Okay. You tokenize the sentence and then you initialize the recurrent neural network's context state. And then for each token, like I returned the coffee maker and so on, you get the embedding, you multiply the embedding with a weight matrix, add to it the bias matrix, and then you take the prior state, which is initialized to 0, multiply it with the context weight matrix. Then you use tanh, and then you essentially calculate the next state that you're going to pass to the next token. Again, I'll not go into all the details here because I've shown this using different examples in the prior episode. If you don't know what this is, I would highly recommend that you go back and look at the prior episode. Okay. Anyway, so I think the key takeaway here is the way an RNN processes this is that it tokenizes a sentence into individual sequence of tokens, and then it processes those individual tokens one after another while passing the context from one token to the other. And the way it does that is something like this. It starts with, you have an RNN, you pass the first token, which is I, and the initialized context that you're passing. And then the context is updated, and then you pass the next token, which is returned, then the next token, which is the, and so on. And essentially, in a loop, it will process all these tokens and then it makes a prediction. Okay. And you do the whole thing about, you compare the prediction with the ground truth value. And if it is not correct, then you backpropagate the error, you adjust the weights and so on. Now let's try to understand why the length of a sequence actually affects how well the RNN can train. So let's go back to our example. Here, there are 16 tokens, and the prediction is made after all the 16 tokens are processed. So essentially, the prediction is made after the 16th token. However, we know just looking at this example that this prediction is heavily influenced by something that happens much, much before, which is essentially at, let's say, token number 2 or time step number 2. Okay. Now, what happens if this length, essentially the select set of tokens that influence the final outcomes, appear much before the end of the sequence, which is where the prediction happens? What happens then? So let's try to see the math behind that. So let's focus on just this part here. The context that is flowing through the recurrent neural network across all the tokens in the sequence goes like this. The current context, let's say H2, is a function of tan H of the previous context H1 times the weight matrix plus the additional, the input value and the input weight matrix and so on. So this is essentially the formula. So you can see that the current value is dependent on the previous value this way, and it goes through a tan H function. Now, in order to make this prediction correct, what you have to do is, the only two levers we have is to adjust these weights, WH weight, which is essentially the context weight matrix, and the WX weight, correct? These are the only two levers we have. Now, how does backpropagation work in a recurrent neural network? Because a recurrent neural network has a loop, the backpropagation not just adjusts the weight once over here, but it adjusts the weight once here then it adjusts the same weights again in the previous timestamp, again in the previous timestamp, again in the previous timestamp, and so on. I actually explained this in the previous episode. It's called back propagation in time. Okay. Now, mathematically speaking, if you look at it this way, let's say the loss, which is the cross entropy loss between the predicted value and the ground truth value, is, let's say, loss. Now, what you're saying is how much weight adjustments can I make to WH and WX in this timestamp so that the loss is minimized. Then I go back, right, which is this one here. Then I go back and say, how much weight adjustments do I again make to the same weights, WH and WX, in this timestamp so that the final weight is less. And then you go back and then you say, how much weight adjustment do I make, so that the loss is minimized and so on. So essentially, you go back like this and you multiply these losses. Like this is basically, you know, high school level calculus, essentially differential equation here. Okay. Now, what happens when the sequence length increases? As you can see, this is a function of how many elements are there in my sequence, correct? Here there are 16 tokens, so it's 16 times you're multiplying. Now let's assume that the gradient of this here is basically 0.3. And let's assume it's the same gradient across all these timestamps, okay, just for simplicity reasons. And by the way, derivative of tan h is always going to be a value between 0 and 1. You can go back and reference your high school level calculus. You'll know that the derivative of tan h is always going to be between 0 and 1. Okay, which means that it is a fractional number. Now, in the first timestamp, it is 0.3, let us say, which means that I'm going to adjust the weight by decrementing it, let's say, by 0.3. Okay, that's the simplest way of understanding this. Now, in the second timestamp, when I go back, that 0.3 gets multiplied by 0.3 again, assuming that each of them have the same gradient. Let's say it goes to 0.3 again. So 0.3, which is a fractional number, multiplied by itself becomes a much smaller than number than 0.3. Then you go back one more step. Now that 0.3 gets multiplied by 0.3 again, assuming it's the same gradient, even for this time step, and that becomes even smaller number. So as you're going behind in your time steps and as you're going to the beginning of your sequence, the number starts to decay very, very rapidly because you're multiplying small numbers. And here, if you notice, this is the place where we said, this input influences the prediction, which is at time step 2. The gradient value is actually very small, almost close to 0, which means that, even if you were to adjust the weight by decrementing it with this value, the weights are not really moving much. And as a result, as the sequence length increases, what you will see is that the gradient vanishes. And as a result, the tokens in the beginning, they would essentially have lesser influence on the prediction that is coming out at the end. Now, again, this is also a very small sequence length. You're talking about 16. Typically, in real life cases, you would have sequence length of 50 or 100 tokens or words, which means that when you get to that size, your gradients essentially vanish. And as a result, the neural network is not really learning. So that is the problem of, RNN, a classical RNN for very long sequences. And one of the reasons why that happens is because the relationship between the current value and the prior value is multiplicative in nature. Okay, you're multiplying the previous value with the weight matrix to get the new value. Okay, and because of this multiplication and because the derivative of this when you're doing the gradient descent is going to be a fractional number always, because tan h derivative is always a number between 0 and 1, you will see that as you're multiplying backwards, this is going to get very, very small. So how do we address this limitation of an RNN where an RNN learns very little from details that appear much earlier in a long sequence due to the vanishing gradient problem? And there is no way for us to store memory of important information that we can reference later as the sequence length increases. We do that by essentially, number one, adding to an RNN a concept of long-term memory, where important information can be stored and referenced back later, and also by addressing the vanishing gradient problem by looking by addressing the multiplicative relationship that exists between the current context and the prior context. This is the multiplicative relationship that exists in an RNN. So by addressing these two, we will be able to solve the limitation of an RNN in processing a very long sequence. That is where a new form of an RNN, an optimization on top of a classical RNN called long short-term memory, also called as LSTM, was introduced way back in 1997. But its popularity was really took off when Google used that in 2015, almost 18 years later, in Google Voice transcription, and they found out that by using an LSTM, they actually could improve the accuracy by 50%. And then again in 2018, Google introduced this concept called Smart Compose in Gmail, where as you're typing in an email, it'll essentially autocomplete not just the next word, but it can finish off the sentence. And the finishing of the sentence was done in a very contextual manner. And ever since then, any popular email service that we use, whether it is Gmail or Outlook and so on, essentially has this feature, and we have been used to it. And all of that is thanks to LSTM. One big challenge with LSTM is that it's a very complicated architecture. If you look at its paper, the 1997 paper where the concept was introduced, it is pretty complicated, a lot of math, and it is very intimidating and inaccessible. And if you look at any of the online articles on LSTM, they show all these pictures with a lot of boxes and a lot of functions like tanh and sigmoid and all that, but they really never explain why any of these things is needed. And as a result, I mean, if you ask, let's say, Perplexity, is it hard to understand LSTM? And it actually says this: LSTM networks are widely regarded as more challenging to understand than many other neural network architectures. And it articulates the reasons why it is so. So, what I thought maybe the right way to understand an LSTM is not first to understand its architecture or the math behind it or even the code, but actually first to get an intuitive understanding of what's really happening. And for that, we can actually use our human brain and how we process long sequences. And once we get an intuitive understanding of that, we can now then map that to actually understanding the architecture of an LSTM as well as the math behind it. So, to do that, I will take a very different approach than the ones used elsewhere to explain how LSTM works or how we can intuitively understand LSTM. I'll use Breaking Bad, which, in my humble opinion, is the greatest TV series ever made, to help us understand the core concepts behind how our brain processes long sequences. And then we will map that to how an LSTM is designed and how it really works. Now, Breaking Bad is a TV web drama that ran from 2008 till 2013. It's made out of 62 episodes spread across 5 seasons. There are about 16 main characters and dozens of subplots. There are several other smaller characters. It's almost 50 hours of content. Now imagine we are binge watching this TV series episode after episodes. And as we are watching across all these 50 hours of content, we start to forget some of the main characters and some of the main subplots. So by the end of the TV series, we will really not be able to make sense of the climax or why it turned out to be that way or why certain characters are behaving a certain way towards the end of the series, correct? So how do we fix that? How does our brain fix that? The way it fixes that is first to we identify what is important information. For example, who are the main characters? What is their motivation? And that builds up over time, episode after episode, context after context, and so on. The next thing we do is we continue to remember the important details, like the subplots among various characters. Why is it that Jesse Pinkman and Walter White behave in a certain way? Why is it that Saul Goodman does certain things? So as these main characters are doing this again and again, we start to remember those details. And the other thing we also do is we don't have an infinite capacity to remember everything. So we also start to forget unimportant details, like some of the subplots, which are there to make the story move forward, but they are not necessarily useful in arriving at a conclusion towards the climax of a single episode or of the entire series. We tend to forget those details. Correct? So how does this help us in understanding LSTM? So let's go through this step by step. So the first thing we need is a memory bank. In the memory bank, we'll have to store important information. Now, how do we add information to this memory bank? So let's say we have something called as a gate that will allow us to add information to this memory bank. And then we also have to forget unimportant information because we have limited capacity in our memory bank. So we'll also need, in addition to the add, we'll also need a forget gate. And what the forget gate does is it'll start removing unimportant information from the memory bank. Now, as you're watching episode after episode, we will filter out the unimportant information from the memory bank. Then we will process the episode and add important information into our memory bank. Now, let's go step by step. Let's say this is the first episode, and in the first episode, we have Skylar, Walter Jr., Walter, Hank, and Murray who show up in the episode. Our memory bank is empty, so there's really nothing to forget. So we add all of them into our memory bank. And let's say, just as an illustration, we will use the screen length or the time they spend on screen as a measure of how important their character is. Obviously, that is not the right way of measuring it, but as an example, I think that'll serve the purpose for us. Okay. So let's do that. So what we do is we essentially say initially our memory bank had none of these characters, so their score was 0. And let's assume that each of these characters in the first episode have equal amount of time they appear on the screen. So we score them on a scale from 0 to 100 as 50 because each one has equal presence in the TV series. Okay. So they are all of equal importance at this stage. Now we move on to the second episode. In the second episode, we essentially have Walter White coming back. We also have Hank coming back, but there are two new characters, Steve Gomez and Jesse Pinkman, who show up in our series. And we also see that the prior characters like Skylar White or Marie or Frank Jr. do not appear in the second episode. And again, we are going back to our measure of how long a person appears in that episode as a score or a measure of how important they are to the storyline. Again, I want to repeat, this is not the right way of measuring it, but it serves the purpose of demonstrating how our brain processes information and how later on an LSTM will build on something like this. Okay. So with this second episode, what we will do is, okay, we see that these characters, Skylar, Murray, and Walter Jr., do not appear. So we have to forget some portions of their score in our memory bank. Okay. And we also see that newer characters are added. So first thing we do is that we decrease the score of these characters that do not appear. Like Skylar White goes from 50 to 25, Mary goes from 50 to 25, and Walter Jr. goes from 50 to 25. We add the new characters that are showing up in the episode for the first time. So Steve Gomez was at 0, he went to 25. And we also see that Jesse Pinkman was not there in the prior episode. His score was 0 in the memory bank. Now it has gone to 50. Why? Because Jesse Pinkman appears a lot more times than Steve Gomez in this episode, as an example. And we see that Walter White comes back into this episode and he also spends some time. He gets some screen time. So does Hank. And we essentially add more score to both Walter White as well as Hank. So our memory bank has now this information for each of these characters. Okay. Now let's get to keep on watching more episode. Let's say we get to the 10th episode. In the 10th episode, let's say these characters appear. You have Jesse Pinkman, you have Skinny Pete, you have Badger, and you have Walter White. Now we'll apply the same thing. Okay, we see that Walter White is appearing in all the episodes and he's basically spending some screen time. So, and so does Jesse Pinkman. And then you have, Badger and Skinny Pete appearing for the first time. So we'll adjust their scores accordingly. And we say that, okay, you know, let's say, here, Badger is appearing for the first time. Initially in our memory bank, his score was 0. We bump it up to 10 because he appears for just a few minutes in the entire episode. We essentially up the score of Walter White from 75 to 100 because the accumulated time that Walter White's character spends on screen has been adding up over the last 10 episodes. Remember, we are at the 10th episode right now. So does, Jesse Pinkman. We essentially up the score from 50 to 75. And what we also do is we start to decrease the scores of people who have not been appearing as often in the first 10 episodes that we have seen. For example, Steve Gomez originally went from 0 to 25, and over the last 10 episodes, because he's not appearing enough, we start to decrease his score, and we go from 25 to 5. Same with, Skylar White goes from 50 originally to 25 to 10, and so does Mary's score go from 50 to 25 to 10. And then we continue to watch more episodes. You get to, let's say, episode 21. We get all these characters. We get Saul Goodman, for example, and his assistant Huel. And then we apply the same logic. We increase the score. First of all, we add new information. So Huel was not there in any of the prior 21 episodes. He's appearing for the first time here. So we add that to our memory bank. We don't know yet how important it is. We'll only know that as his character starts to reappear in the future episodes. And what we're doing here is, even Saul Goodman appears for the first time. So we essentially give him some score. We add him and we give him some score. And we start also to downscore those characters that are not really showing up that frequently in the last 21 episodes. So we continue this. We get to the 35th episode. Newer characters get added. Existing characters, the scores increase, and some of the existing characters, the score starts to decrease. For example, Huel appears sparingly in the episodes, so we start to decrease his score. Same with Badger and so on. So finally, we get to, let's say, episode 60, and more characters get added. So we add them to the memory bank. We adjust the score of existing characters, either up or down. So we're essentially down, meaning we are forgetting, or rather, we are downsampling their importance. So we're forgetting information about them. And we are adding newer characters, but we are also up scoring certain characters that are already in our memory bank, because their importance starts to show up over all the episodes. Now, finally, we get to the end of the series, and our score essentially looks like this in our memory bank. And this is, in a way, like a probability distribution of how important each character is to the entire series. So we essentially take that, and then we started with a memory bank of all zeros. We could essentially arrive at a memory bank that has a probability distribution of how important each of these characters is to the entire storyline. So the key takeaways here are: you start with a concept of a memory bank. That's how our brain functions. And then as we are watching things, we start to add those into our memory bank. And as we are continuing to watch, we will remove those things that are not really relevant, because we do not have infinite capacity to remember everything. We will start to remove those that are less relevant, and we will increase the score of those things that are more relevant to the storyline. So this is the core idea behind how you process long sequences. When there are several subplots within it, there are several characters within it, and so on. Now, how do you go from here to actually understanding LSTM? Let's study that next. Let's start with a high level architecture first. So let's actually start with a classical recurrent neural network. In a classical recurrent neural network, which we have seen in the prior episode, you could actually unfold the neural network, and it looks like this. The sequence is processed one element at a time, and you'll start with an initialized state, and that gets passed along with the sequence input, and so on. So when you want to take this RNN, classical RNN, and convert it into an LSTM, we will need a few things. Number one is that we will need this concept of a memory, a long-term memory, which, it's like a whiteboard if you think about it. By the way, an LSTM is an optimization on top of an RNN. At its core, it still has this concept of unfolding and processing an input by first tokenizing it into a sequence and then processing it individual elements of a sequence at a time. So it's basically, an LSTM is a form of an RNN, an optimized form of an RNN. Okay. So our goal now is to take this architecture and convert it by adding a few things. Number one is that we add this concept of a long-term memory. This context state that exists in an RNN, which in an LSTM is called as a short-term memory, that continues to exist. But we also need to capture this long-term memory. That is what this C what you see as C here, that's what it stands for. It's called cell state in the literature. Now we unroll it just like you unroll an RNN, and both the short-term memory, which is represented using H, as well as the long-term memory, which is represented using capital C, get passed to each of the LSTM cells. Now we will need to have three gates in each of these cells. The first gate is it will remove unimportant information from our memory. So it will remove unimportant information from our long-term memory. The second one is the add gate, which will add important information to our long-term memory. And then the third one is what is called as an output gate, which will pass the information that is, connecting the context that is flowing across all the words in a sentence. Okay. Now, basically the same cell again, because it's unfolded, it appears again and again, and the long-term memory and the short-term memory are the ones that tie all these things together in a sequence. Okay. So in order to understand LSTM, we actually have to understand five things, five concepts. One is the hidden state. This hidden state also exists in a RNN, and this is the one that passes the context between adjacent words in a sentence. To that, we are adding this new concept called as a cell state, which is a long-term memory. So think about this as a whiteboard that is tracking key characters or key subplots across multiple episodes and seasons and so on. Then you'll need to have the gates. The first one, as I said, is a forget gate. It's a knob that controls how much unimportant information we have to forget. Okay. Then we have to have an input gate. It's a knob that controls how much important information we actually keep in our memory bank, in our cell state. And the final one is the output gate, which essentially tells how we pass along the hidden state, the context from one word to the other word in the sentence. Okay, as you're processing that sentence. So, first thing we need to actually address here is how does an LSTM actually know what is important? Because we are saying that the long term memory keeps important information, and the gates essentially modulate how much of that important, so-called quote unquote the important information gets added or removed. So how does an LSTM even know what is actually important? The interesting thing is it actually does not really know what is important, but it learns it through the training process. And the way it does that is, first is it starts with some initial randomness. Okay, you initialize the weights to some random values, and we'll see what are those weight matrices shortly, but it initializes it to random. So it really does not know anything about what is important. The next thing is, as we are training, we show that network many examples. Let's say we are doing a network that is being trained on movie reviews, and to identify the sentiment that's conveyed by that review, you show it many such movie reviews, and you pair that with the pre-labeled, whether that label says the movie is good or bad and so on. So the LSTM actually looks at all that training data. Then it makes predictions, and if its predictions are wrong, then we back propagate that through the network so that the weights are adjusted. Okay, so this is nothing different than any of the neural networks that you have studied so far. But what will also happen is that because of the way the LSTM is designed, it will actually start to recognize patterns. It will basically recognize things like if there are words like, let's say, for example, amazing and terrible consistently, then it will say, okay, these kind of words seem to correlate more with certain types of sentiments. If the word amazing exists, then there is a likelihood that that review is positive. If the word terrible appears, there is a likelihood that the review is not good. So the LSTM starts to recognize this pattern and build things around that by recognizing these words and their correlation with the sentiments that they convey. They also, understand that there are certain words that can flip the meaning of, subsequent words. For example, if it sees something like a despite or however, it'll start to learn that, okay, these things, are flipping the meaning of what appeared before these kind of words appear. Okay. It learns that. And then we have these gates, the input and the forget and the output, which the LSTM learns, when to open and when to close, how much to open and how much to close, based on how its predictions are relative to the ground truth value in the training data set. Okay? And then, it'll also start to look at, what are those words which are strong indicators of a positive or a negative or a neutral sentiment. And all this goes back to, its prediction and the ground truth value that says, what is the actual sentiment that's being conveyed by the movie review. So using these gates and this long-term memory and the short-term memory and all of those things, the LSTM starts to figure out what is important and what is not important. Maybe another intuitive way of looking at it is, if it is not important, okay, then its prediction will be off. If it is, let's say it is not important and the LSTM is not, downscoring, those words, then its prediction is going to be off. And if it is important and it is not upscoring them, even then the prediction is off. So over a lot of back and forth through the forward progress as well as forward pass as well as the backward pass, the LSTM figures out what is important and what is not. Okay. So now let's dive into the architecture. Again, the quick recap. The LSTM looks like this when it's unrolled. You have this long-term memory passed as a cell state, the short-term memory, which is denoted as H here. And each of these cells has these three gates. There's a forget gate, input gate, and an output gate. Okay. Now let's double click and see what each of these gates do. Okay. So by the way, these are the different formulas that actually express, how these gates operate. And just by looking at it, somebody who's new to this will start to get intimidated because there's a lot of this, there appears that there's a lot of math here, a lot of formulas and so on. But actually, if you understand this intuitively first, then you'll see that this is actually not really that complicated and it actually clicks because there's a certain way in which this thing is designed that is very natural. Okay, so let me explain that. So the way I will explain this is I will go through each of these gates, okay, and I'll explain what is really happening and why is it happening that way and why is it that these specific arrangements will actually, let's say, enable the LSTM to forget unimportant information or enable it to add in important information into its long-term memory and so on. Okay. Let's start with the forget gate. Again, the forget gate is forgetting unimportant information from our long-term memory. Okay. So we'll focus on this gate here. Okay. All right. So the first thing. So this is the token that's coming in at time step some t. Okay. And the previous hidden state, the short-term memory state is ht minus 1. And the whiteboard, the memory that we have is expressed as ct minus 1. Okay. Now, what we have to do in the forget gate is that we have to forget unimportant information from the long-term memory. Okay. Now, the first thing is how is the input actually propagated into this gate? The way it is propagated is that you take the embedding, the word embedding for this token, and then you concatenate it. The matrix here, this matrix here, this matrix is the embedding, word embedding for this token. You concatenate that with the previous short-term memory state. Okay, that's what you do. So it's basically nothing but concatenating two matrices. You take xt, the word embedding for this token, and then you concatenate it with the short-term memory multiplied with the learnable weight matrix that we have here. This part is exactly like how you have it in a RNN, a classical RNN. Now this is the input that goes to all the gates, by the way, Z. Okay, it's a concatenation of the token plus a multiplication of the previous hidden state with the weight matrix for that, learnable or trainable weight matrix for that. Now what you do is that the forget gate is actually calculated as this input, which we'll now start calling Z, okay, going forward. This Z times another trainable or learnable weight matrix called WF, which is weight matrix for the forget gate. Okay, that's what it does. And then you take this gate's value, which is calculated as a sigmoid of WF times this input Z, and you multiply it with what is coming in through the input here. Okay, CT minus 1. Okay, so let's study this a little bit more. By the way, this when expressed fully is C forgotten is that, which is basically our long-term memory or the whiteboard is basically what was there in the whiteboard so far times the value of the forget gate. Okay, let's double click that further. Okay, this is what it is. Now the first thing here is the information from the previous episodes. So let's say the previous episodes you had Skylar White, you had the Walter Jr. and you had Walter White and you had Hank and you had Mary. Okay, this is what HT minus 1 is. Then you information from the current episode, which is in the current episode, you have Walter White appearing, you have Steve Gomez appearing, you have Hank reappearing, and then you have this new character, which is Jesse Pinkman appearing. Okay. Now, what is there in our whiteboard currently, our long term memory? You had, so far what we have seen is that Walter White and Skylar White and, Walt Jr. and Hank and Mary all have equal scores of 50, 50, 50, and so on. Now, what you're doing here is you have to forget some portions of these three characters because they don't appear in our current episode. See, in this current episode, only these characters appear. You have to forget this. So, how do you do that mathematically? The way you do that mathematically is that if you can multiply these values with something which is a value between 0 and 1, you can essentially decrease their score. Because what is it that you're doing? Forgetting means what? You're decreasing the score of these characters. One great way of doing that, if you want to kind of get a number between 0 and 1 to multiply with these cells, is sigmoid function. Because sigmoid takes any value and it squashes that value, however big or however small it is. It squashes that value into a value between 0 and 1. That's what sigmoid does. Okay. Now, what you could treat it as, okay, if the sigmoid value that comes out is 1, then means that you don't forget anything about this person. If the sigmoid value is, let's say, 0.9, it means that you forget 10%. Say a number multiplied by 0.9 means that 90% of that value is still retained, 10% is forgotten, correct? And so on. If the sigmoid value is, let's say, 0.2, which means that you are retaining 80%, so you're retaining 20% and you're forgetting 80% of that information, because a number multiplied by 0.2, essentially it will keep 20% and the remaining 80% is thrown away. So you know that sigmoid function is a great function that can be used if you want to forget or downgrade the score of those values that already exist in our whiteboard. That is the reason why the forget gate essentially uses a sigmoid. But it is sigmoid of what? It is doing a sigmoid of the input that is coming in, and that input is basically a mix of a concatenation of the previous state that's flowing through our network so far and the current, at this time step, the current value, correct? XT and HT minus 1. So once you do that, you can essentially downsample and forget the relevance of certain characters from our long-term memory. Okay. Now here, if the value of, let's say, Walt is not changing, it's because you want to not forget anything about these characters because, they reappear in our current episode. So essentially the sigmoid, you should swing it more towards 1, both for Hank as well as Walter White. Okay. And you have to swing, let's say, the values for, Skylar White as well as Walt Jr. and Murray by, 50%. So that you would essentially decrease their score. Okay. How much percentage you would increase and decrease, it all comes down to, you make some prediction. First of all, this weight matrix here, WF, is the one that is influencing this, correct? This is the one that is influencing it. So what you have to do is that since this is randomly initialized, initially you will make all wrong assumptions, and you'll either, in fact, you might end up, forgetting some portions of Walt and Hank as well, which you should not. And you might actually increase the weight of, or rather keep the weights the same of, Skylar and Murray and so on. But as we compare our prediction with the ground truth value, you'll realize that, hey, the way we are swinging the scores of these individual characters is incorrect. And over time, we will start to swing it in the right direction so that, we forget less important information from our long term memory. So, one key thing to observe here is that this long term memory is only decreasing the scores of people that it has deemed as less important as it is processing the current episode. But what happens to these new characters that are not there in the prior, or long term memory? That's not here. And the reason it's not here is the role of a forget gate is to take what already exists, which is ct minus 1, multiply it with what is coming in the current episode, along with what it has seen so far. Okay. So it will kind of change the values of those characters that are already in the whiteboard. There is no provision here to add anything, correct? It's only changing the scores of characters that already exist in our whiteboard. So that is what the forget gate does. Okay. So when the forget gate is done executing, it will emit a updated value of our long-term memory with scores adjusted so that less important characters, their score starts to go down. Important characters, their scores remains the same. Okay. We also have these two characters, Jesse Pinkman and Steve Gomez, appearing for the first time in our episode, and but they don't appear in our whiteboard. So we have to add them to our whiteboard. How do we do that? For that, we have to use the input gate. And what is the purpose of the input gate? The input gate adds important information to our long-term memory. So now we'll focus on understanding how this gate works and how the math behind it works, the intuition, as well as actually what is really happening when these gates actually processes this information. Okay. So by the way, what is the input to the input gate? The input is basically the same, the concatenation of the current tokens embedding, its text, for example, and the previous state, correct? And now this input actually goes into two functions. One is a sigmoid function. You see, I represented this using what I call as I what, which is what information needs to get added. And the second one is I how much, which is the input how much, which is how much of that information needs to get added. By the way, the literature doesn't call it out this way, but I think that expressing it like this makes it easy for us to, kind of do a mapping behind, do a mapping between the math and what is really happening. Anyway, so the input goes through what needs to get added and how much of it needs to get added. And then using some math here, which we'll explore very shortly, we will update our whiteboard or long-term memory. Okay. So this is the function for the input gate. So the first thing is the previous state that is flowing through is our ht minus 1. The current episode has these characters hxt, correct? Now, the existing memory, the long term memory, will have these values. Remember that it has already gone through the forget gate and we have suppressed the values of these three characters because their importance is less as we are processing episode after episode. So, this is going to be our existing, our current updated whiteboard. Okay. Now, this is the information that you're adding. You're adding to the whiteboard here for the first time. You're adding here. Okay. You forgotten unimportant information. Now you're adding important information. Okay, let's study this important information adding now. The first thing is a sigmoid. So sigmoid basically, which is represented as this I what thing, is what information needs to get added, what is important that needs to get added. And again, a sigmoid is a great way of taking any value and squashing it between 0 and 1. So if it is 0, it is not important. If it is 1, it is very important. So you would essentially use that sigmoid function over the input, which is Z, and you'll use a trainable weight matrix WA, and you will multiply that and take a sigmoid of that. That will tell us how important is this new information that is coming in, and it will score it between 0 and 1, and that's what you're going to get. Okay. For example, Steve and Jesse both appear for the first time, so obviously they need to get added. But Jesse has 2x more screen time than Steve, so we have to amplify, Jesse's score more. Although both of these are important information and needs to get added, we actually use the sigmoid function to swing, a higher value to Jesse than to Steve. Now you also need tannage. What the tannage does is it'll also say for the existing, characters that are there in our whiteboard, how much do we amplify their signal or how much do we change their signal strength? Basically, Hank and Walter are already there, and again they appear in this episode. So we don't have to add them, but we have to amplify their signal, further. And tanh is a great way to amplify it or suppress it based on, this function of tanh, which takes any number, however large or however small, and squashes that between a -1 and a 1. Okay. So it's a great way to kind of modulate the strength, signal strength of individual, characters that are there in our long-term memory. So that's essentially what is happening over here. So you take the multiplication of these two, the I what, so what is important and how much of that is important, you multiply that, and then you add that to the information that you have gotten from the forget gate. So you update your long-term memory based on that. Okay. So at this point, what has happened? So for number one, you added the new characters. You added Steve and you have added Jesse. Both of them initially had a score of 0. You added them and you have made the scores appropriate based on, you know, like what is their importance to the plot line. Okay, so Steve is less, so you essentially add the sigmoid essentially swings the score towards, let's say, 25, and Jesse is more, so it gives him more score and swings it towards 50. Walter White and Hank appear again, so as a result, you actually swing up their score further, and you essentially increase it from 50 to 75 for both of them. Okay, so at this point, we have updated our long term memory. We have taken out unimportant information using the forget gate, or rather, we have suppressed it, and we have added important information which doesn't already exist to our long term memory, as well as amplified the signal strength of those that are important using the tanh function. So now we have an updated long term memory. Okay. Now let's get to the output gate. Now, output gate this is basically the short term memory, and you need to pass that short term memory to the next element in our sequence. So, how do we do that? So, we'll focus on this gate right now, the output gate, and this is the math for that. It's relatively much simpler than the previous two ones. So, let's understand this. What is the input to the output gate? It's the same thing, the concatenation of the previous short term memory with the word embedding for the current input. That is what you pass. And then actually, let's expand this. Okay. So the updated short-term memory is calculated by the output gate as following. Sigmoid of the input that's coming in. Again, the input is a concatenation of the current input tokens embedding and the previous short-term memory. And then tan h of the whiteboard, which is the long-term memory that we have calculated in the previous steps. Okay. Remember one thing. At this stage, when you get to the output gate, pretty much the long term memory is all taken care of. We have essentially computed the changes that need to be made to the long term memory by eliminating what is unimportant and adding what is more important. Correct? So that doesn't get changed in the output gate at all. Only thing that gets changed in the output gate is a short term memory. So this is, let us say, our long term memory that it's set to these values. The previous short-term memory is this, the current input is this. So what the sigmoid does is, again, how much do we amplify or suppress the weightage of each of these characters in the short-term memory as they are progressing from episode to episode or one element of the sequence to the other. Again, sigmoid is a great way to squash the values between 0 and 1. So that's why sigmoid is used here. And then you actually multiply that with the value that is there in the long term memory, because we also want to see the information that has appeared that has been accumulating so far, that has appeared in the previous, let's say we are in the 40th episode. The long term memory is carrying information that is there way back, all the way from the first episode and so on. So we also want to take that signal strength for each of these characters and multiply that with the short term memory. That's why you use tanh. Again, tanh ensures that the value is bounded between a -1 and a +1. Okay, that is the reason why a tanh is used on the long term memory. And you take the multiplication of both of those things. So just to summarize our understanding of LSTM, what is happening here is, in an LSTM, you have this long-term memory and then you have the short-term memory, and you pass this through the LSTM cells through three gates: the forget gate, the input gate, and the output gate. The long-term memory basically carries accumulated information or the context over long time periods, and it uses the forget gate to suppress unimportant information, uses the input gate to add new or amplifies important existing current information in the long term memory. It has no direct role in the output gate has no direct role in manipulating the long term memory. It has an indirect role because the output gate changes HT and the which is the short term memory, and the long term memory also depends on the you know the short term memory, because if you look at the value z is a function of both the short term memory as well as the current input. There is no direct input or direct role that an output gate plays in manipulating the long term memory. Now, summary again, the short term memory essentially carries the context that is flowing across shorter time steps. So it's more influenced by words that appear more. So the forget gate has no role to manipulate the short term memory. The input gate has no role to manipulate the short term memory, at least no direct role. It has an indirect role because, again, the short term memory also depends on CT. CT depends on the forget and input gate, but there's no direct dependency between the manipulation of the short term memory H with forget gate or the input gate, but the short term memory is updated using the output gate. Okay. Now, why does something like this actually address the vanishing gradient problem? Remember, I told you that there is a vanishing gradient problem where if the sequence length is too long, the gradient descent algorithm essentially, as it is updating the weights of these matrices, of all these matrices, as it's progressing backwards in time through all the time steps, the gradient value starts to go so small that they go to zero, and as a result there is no change that is happening to these weight matrices. And the reason we explained that also is because in the classical RNN, there's only short term memory, and the short term memory has a multiplicative relationship. The current value is a multiplicative relationship with the previous value, and when you take the gradient of this, essentially the partial derivative of this, it becomes an exponentially decaying value, because a small value multiplied by another small value is a much more smaller value, multiplied by another small value is much more smaller value, and so on. And there is no way to add information to the short term memory. That's where the long term memory comes in, because even in a long term memory you have this multiplicative effect, which kind of, as you're doing back propagation in time, the gradient value becomes much more smaller and tends to go towards zero. And as a result, in the previous time steps, the change in the weight matrices is going to be less. However, the long term memory also has an additive property. Because of the additive property, what will happen is, regardless of how long the sequence starts to get, you have this addition, and that addition protects itself from making the gradient so small that the weights do not change. Okay. That is the actual intuition behind why the vanishing gradient problem does not really exist to the extent that it does in a RNN. Of course, if you give it a very, very, very long sequence, let's say you give it a sequence of 1,000 word sentence and things like that, even there you would see that an LSTM will start to struggle, because, again, regardless of whether you are adding or not, these values, essentially because of tan h and all that, they are smaller values. Any value is usually between -1 and +1. So as you're going back in time across all these 1,000 time steps, you'll see that the values start to diminish. But 1,000 is an unrealistically long sentence. So for sentences that are, let's say, 50 or 100 words, which is also pretty large, what they have observed is that because of this additive thing that's happening within the long term memory of a LSTM, you don't have the vanishing gradient problem that an RNN has. Okay. Now let's revisit this important thing again, just as a quick recap. As we said in the beginning, LSTM inherently does not know what is important. It learns this through the training process. Initially, it starts with random data, then it trains. You give it a lot of examples, and then it trains over that. It back propagates, updates its weights, and so on. But what happens here is that because of this long-term memory and because the gradients are not vanishing, it will start to make correlations that even words like amazing and terrible, even if they appear much earlier in the sentence or much earlier in the sequence, because of the additive property of the long-term memory, it will be essentially start to associate the right sentiment. How does it know what the right sentiment is? That is available as a ground truth value, right? The ground truth label for, let's say, of the review sentiment that is there in our training data. So it'll be able to make that association, even though these words like the words that influence the actual sentiment, things like amazing and terrible, even though they appear much earlier in the sentence. It also starts to recognize that there are certain things that you could have a very positive, let's say 90% of the sentence all saying positive things, and then towards the last 10% of the sentence you have words like despite and however that flips the meaning, correct? Because of the short term memory with the long term memory, it'll know that there are certain words that trigger a flip in the sentiment. So that's another thing, that the combination of the short term and the long term memory as it's architected or designed in the LSTM helps the network to learn. And of course, the gates enable it to kind of figure out how much of the information to pass in, how much of the information to suppress, what gate to open, what gate to close, and so on. Okay. So over time, when you train the LSTM with a lot of data, it actually figures out what is important, what is not important, what words trigger flipping of the sentiment, what words trigger, pushing the network weights in such a way that it is more aligned with the ground truth values and so on. Of course, our web series is not complete without actually implementing the concepts that we have learned. So let me show you how you would implement an LSTM. Obviously, when you're using it for practical production use cases, you would use library functions that have been optimized. But before you start using a library function, let's actually hand roll an LSTM to understand its core concepts better. Okay, that is the best way to actually understand concepts, not just using library functions. Okay, so let's look at that. So this is our familiar picture, the LSTM cell with all the forget input and output gates, with the long-term memory, which is called as a cell state, and the short-term memory, which is the HT. Again, these are the formulas that show you how these gates operate and how these values are manipulated. So I hand-coded this LSTM implementation using just NumPy, and it helps us actually figure out how would you translate this code from concepts to actual implementation. Okay, so what I have is I'm initializing all the weight matrices WF, WA, WB, and WO. I'm initializing them to random values. Just like in any neural network, you start off by initializing it to random values. I'm also initializing a neural network also needs to have bias values. I'm also initializing the bias values. One thing that you notice here is that in any of the formulas or any of these pictures, I don't show the bias matrices. That is only because it's much easier to see a picture if it's not overcrowded with all these matrices. So I've skipped that. But in reality, you also need, with every weight matrix, you also need to have the bias matrix. Why you need to have a bias? I've explained this very clearly in episode 1 of season 1. So if you do not know why a bias is needed, you can go back and reference that one. Okay. But anyway, so I'm initializing the weights and the corresponding bias matrices all to 0. Now all to random. The bias is always initialized to 0. I also explained this in season 1, episode 1. Okay. We also, of course, when you have to make the final prediction, you need to have an output matrix. So that is also initialized to random, and the bias for the output is also initialized to zeros. Okay. All right. So across multiple training epochs, let's say I'm training across 10,000 epochs. I take a sentence, I take a collection of sentences, then I take one sentence. And what we do is that we tokenize the sentence. Okay. You tokenize the sentence, and then you process the one word of the sentence at a time. But before that, you need to initialize your long-term and short-term memory. So the short-term memory, let's say, is called hbrief. I initialize that to 0, which is this one here. I initialize it to 0, h0 is 0. The long-term memory or the cell state is initialized also to 0. Okay, now I have this. I also keep a record of all the manipulations that are happening to the long-term and short-term memory in an array here. Okay, and also the predictions that are coming out of these individual LSTM cells in this array called predictions. Now, for each word in our sentence, I've tokenized this, let's say. For each word, I have to get the embedding because, again, neural networks do not understand text, they only understand numbers. How do you get a numeric representation of a text? You get that using word embeddings. I explained that in season 2, episode 2. You can go back and reference that if you don't know what this is. Okay. So I get the word embedding for that word. Initially, I start at T0, which is the first element in the the sequence, which is the first word. Then I have to concatenate that, right, with the previous short-term memory. So it's basically array concatenation of the current word embedding and the short-term memory. Now that is what I need to pass through each of the gates. How do I pass that through the forget gate? I take the combined value, multiply it with the weight value, WF, right? Combined, multiplied with WF. Add to that the bias for the forget gate and take a sigmoid of that. That's what is happening here. Sigmoid of Z times WF. Z is concatenation of X in the short-term memory, correct? And then you add the bias value and take a sigmoid of that. That is your forget. Okay. What is input? Input is you take Z, you take a sigmoid of the combined Z times WA, which is this, combined is Z, add that to the bias and you take a sigmoid of that. This is I what. What information are you adding to the long-term memory? Multiplied with how much of that information or how much of the signal strength of that information needs to be added, which is done through the tan H. Tan H is again the same input multiplied by its own weight matrix WB, added to the bias matrix there, and you take a tan H of that. And you multiply these two, so you will get the signal strength as well as what needs to get added to the long-term memory. Now, the output gate's OT value is calculated as what? Again, the combined Z value, which is Z again is the combination of the word embedding at the current timestamp with the previous short-term memory with its own weight matrix called WO and the bias matrix, and then you take a sigmoid. That's OT. Okay. Now, you have to manipulate the long-term memory. How do you manipulate the long-term memory? Long-term memory CT is the previous long-term memory multiplied by the forget gate plus the input that is coming in. So what is forgotten, or rather what information needs to be forgotten, add to it what information needs to get added, and that becomes your new long-term memory. And your short-term memory is what is the output gate, the value of the output gate, times how much of the long-term memory values also influence the short-term memory. That is your updated short-term memory. Okay. From this, you would make a prediction. Yeah. And you store that prediction. If you're doing just sentiment analysis, or you're doing predicting the next token in a sequence and all that, you really don't need to store these intermediate predictions that come out of the each time step. You only need that when you're doing language translations, where each word needs to be translated into a corresponding word in a different language and all that. Only then typically you store the individual intermediate predictions. Otherwise, you're only interested in the final prediction. Anyway, here I'm just storing it just as a illustration. Okay. And I'm also storing the short-term memory and the long-term memory as it's getting updated. Okay, so now I pass this updated short-term memory and long-term memory back to the next token in the sequence. So you go and pick up the next token or the next word in the sequence, go through the same motions again. Okay, then go to the next word in the sequence, go through the same motions again and again and again till you're done with all the words in the sequence. Okay, now once you're done that, you have gotten your prediction and you have to compare how you are predicted with the ground truth value, and that will give you a loss. You use a loss function. Typically, the loss function is a cross entropy loss function. And when you get that loss, you essentially back propagate that loss. Again, back propagate in time because you have to go through first adjust all these weights WO, WB, WA, WF, and so on in this time step. Then you have to back propagate adjusted in this time step. Same weights, again adjusted in this time step, back propagate and adjust in this time step, back propagate, adjust in this time step, and so on. That's where you reverse it and you back propagate and adjust the weights in reverse order. Again, because of this additive function here, you see that even for longer sequences, this weight values, essentially the gradients do not, for the long term memory, do not go down to zero. So you do not have the vanishing gradient problem that is inherent in a classical recurrent neural network. So this is our implementation of a LSTM. Now, where are we going to draw this boundary? Is the boundary for where you want to capture the short and long term memory across a sentence? Is it across a paragraph? And so on. So for that, let me illustrate that using, you know, how you see this in the context of very large, input data. So let's say that you have in a book series, let's say the Harry Potter book series, which has seven, books in that series. Now, each of those books, so seven books in the series, each of the books has several chapters, each of the chapters have several paragraphs, each of those paragraphs have several sentences, each of those several sentences have several tokens. So, do you capture the long term context on every book or every chapter within that book, every paragraph within that chapter, or where do you capture this? So, the way to look at this is if you have hierarchical information like this and you would like to make sense of, okay, for example, what would be if you're trying to understand the sentiment of a single sentence? You obviously need to capture the context around each sentence, correct? But let's say you want to understand the sentiment of a paragraph, then you obviously need to capture it at a paragraph boundary. But what if you want to say, hey, what has really happened in this chapter? Then you need to capture the context around all the paragraphs across all sentences within that chapter. Similar to that, if you want to say, hey, what really happened in, let's say, Prisoner of Azkaban as a book, then you'll need to capture the context at the book level. So when you have hierarchical information like this, the way you would process this is essentially to have multiple LSTMs. Okay. Which is what I wanted to illustrate here. So essentially, I have one LSTM on a book for every book. Then I have, then a chapter based LSTM. Then I have a paragraph based LSTM and a sentence based LSTM. And what we do is that, you basically take all the book series, then you break up take each book in that book series, you break it up into each book into its individual chapters. Then each of those chapters, you break it into individual paragraphs, and each of those paragraphs, you break it into individual sentences. Then you break each individual sentence into its own set of tokens. So the inner loop essentially then becomes processing an LSTM on a sentence boundary. So which means that you reset your long-term and short-term memory for that, the sentence LSTM. And what you do is that, okay, you get, let's say actually, let's look at this. So what you have done here is, let's say you start with the inner loop. Okay. So innermost loop, which is every sentence you're processing. Now, when you're processing every sentence, you would basically say, okay, I'm going to split every sentence into its individual tokens. And I'm going to basically get the word embeddings for each of those tokens. Because again, neural networks do not understand text, they only understand numbers. So you need to get word embeddings for each of those textual tokens. Okay, so that's what you capture in this token embeddings. And that is what you pass as an input to your sentence LSTM. Okay. And those token embeddings go in and you process it like we have seen before. You go through the forget gate, input gate, and so on. You process the long term, short term memory, update it, and you go through all the elements or all the tokens in the sentence. And what you pass back is basically the short term memory or the context that is flowing across all these words in the uh, sentence. Okay. Now that you would store for each sentence, you will store in something called as a sentence embedding, because now you have to process it at paragraph level. So you've gone through each sentence. Okay. Each sentence it's emitting out its updated in a short-term memory. You add that to the sentence embedding matrix, and that sentence embedding matrix essentially becomes input to your paragraph level LSTM. Okay. And then you run the same thing, same LSTM logic across the paragraph. And each individual paragraphs for each of those things, the short-term memory is actually captured in another array called paragraph embeddings. And that becomes an input. The paragraph embeddings becomes an input to your chapter level LSTM and so on. Now, one question, why are we actually using the short-term memory and not the long-term memory? The reason is number one is that actually the short term memory, if you go back, let's just say, go back here. So you see that the short term memory is basically already capturing the information that is there in the long term memory. So that's the reason why you use the short term memory in propagating the context and the embeddings for the next LSTM in our hierarchy. So this is how you would process, things that are hierarchical in nature. This is a textual example, even for time series data. Let us say that you are capturing the system metrics, CPU utilization, memory utilization, storage IOPS, network packets per second, the database queries per second, all those individual metrics. Let's say you're capturing it every second. Okay. So you can say that, I will create a sequence window of, let's say, every 60 seconds to kind of understand what's happening in my system every 60 seconds. But you'd also like to sometimes make a query and say, hey, I want to understand what's happening in this hour boundary or minute boundary or, day boundary or week boundary or month boundary and all that. So there's a hierarchy there. So what you can do is you can essentially structure this as multiple LSTMs. You would have one LSTM that's tracking information on a per second basis, another LSTM that is tracking information on a minute basis, another LSTM on an hour basis, another LSTM on a day basis, another LSTM on a week basis, another LSTM on a month basis, another LSTM on a year basis, and so on. So you have all these hierarchies. So if you want to make the right prediction, what has happened, let's say, what is going to happen in the next minute, you would use the minute LSTM. Although you have captured the individual data across every second because of this way hierarchical processing, you will use the minute LSTM. Let's say you want to make a query and say, what's going to happen next week? You would use the week LSTM. Okay. Next month, you'll use the month LSTM. Just like in the case of these books, if you want to understand what has happened in this chapter, you would use the chapter LSTM. What's happening in this paragraph? You'll use the paragraph LSTM. What's happening in this book? You'll use the book LSTM. So that's how you need to think about data that has hierarchy built in. Okay. Now let's see a actual coding demonstration of how you would use LSTM in your own coding projects. So for our coding project, what we will do is we'll build a LSTM model that can understand news articles. And once it has done processing a news article, we'll give it a short prompt and we will ask our LSTM to complete the sentence. Now, what I'm going to do here is I'm going to import the necessary libraries. Then I'm going to be downloading a article from the internet. I'm going to be downloading this article, which is basically a news report or briefing or statement that was put out by the White House when India's Prime Minister Modi had visited United States. This came out in February 13th of 2025. Okay, let's use that. It's a decently long article. And we want to build a LSTM that can process this article so that if we give it a few keyword prompts, it can complete the sentence for us. Okay. So what I will do is I'm going to download this article. Okay. And I'm going to extract just the text from it. And for that, I'm using, pre-built Python libraries like Beautiful Soup to do that. Okay. It's going to parse the HTML, take out all the necessary tags, and just give me just the text that is there that represents this article. Okay. So this is the text. Right. Now, what I'm going to do is I'm going to break this long text into individual sentences, and I'm also going to tokenize this text so that I can build my vocabulary. So I've done that, and I've seen that the maximum sentence length in this article is 68 tokens long. And the total number of unique words that I see in this article is 1050. And these are the different unique words. So this is essentially my vocabulary. Okay. About a vocabulary of size 1050. Now, LSTM is an optimization on top of a recurrent neural network, which means that just like an RNN, you will need to take your input and make sequences and pass those sequences to the LSTM. I showed you how that is done using various examples in the previous episode, season 2, episode 3. So if you do not know how that is done, I will not repeat it here, but you can go back and reference that. But I've just written a very small piece of code here that will take all this information and it will convert this into all these sentences into sequences that can be fed into my LSTM. Now let's build by the way, when it's processed, it looks like this. 000 is all padding. I'm padding it shorter sentences with pad tokens, which have a token ID of 0 in our vocabulary, so that each of my inputs to my LSTM is of maximum sentence length, which is 68 here. Okay. You can see this here, 68. All right. So that's all I'm doing here. And I'm also producing a ground truth value, which is the next token in, in that particular sequence. Again, I don't want to go into the details. I actually explained this using multiple examples in the previous episode. You can go back and reference that. Okay. So now that I have tokenized it and I've also converted all my sentences into sequences, I'm going to be building my LSTM neural network. So the way I do that is I will use the TensorFlow Keras, sequential the module, and then I'm going to add an embedding layer. Remember that a neural network needs to convert text to numbers. So that is done through word embedding. So I show this in the episode 2 of season 2 as well as episode 3 of season 2. All I need to do is I add an embedding layer which takes the total number of words that are there in my vocabulary and whatever the embedding dimensions that I'd like to learn, which is 300 here, and what is my maximum sentence length. That is one layer. And then I create an LSTM layer. This one will essentially create the LSTM model that I showed you architecturally. And this 150 essentially says that the weight matrix that it creates is of size 150 by 150 cells. Okay. I'm predicting the next word because again, what is my goal? My goal is that I want the LSTM to read all these sentences and start predicting the next word. And in a loop, I can keep on predicting next words to form sentences. So how do you predict the next word? You predict that by softmaxing across all the words in your vocabulary. This is again something that I've explained in multiple episodes. But if you don't understand this, you can go back and look at the previous episode on RNNs, and it explains clearly why we do this here. Okay. Anyway, so this last layer is an output layer that is using softmax as my output function. And for the loss function, I'm going to be using the cross entropy loss function with an optimizer of Adam. Okay, let me compile this. If you notice here, this is I've not really run this yet, so it's not really formed all the connections yet. But now let me run this. Okay, so when I run this across 100 epochs with a batch size of 30, you see that the loss is starting off very high at 6.5. Remember that the loss needs to go down to a very small number, typically 0.00001 or something like that, which is when you know that your neural network is trained well. So here it starts off very high, but across multiple epochs, the loss is going down, it's converging down to a smaller value, which is what we want, which means that our neural network is actually learning the patterns that are exhibited by the different words and sentences that are there in this news article. So at the, let's say, 45th epoch, the loss has gone to about 0.17 something. It started at what? It started at 6, I think. Yeah, 6, and it is going down. Yeah, let it go down. Let it run till 100 epochs. By the way, this is a very small sample set. Ideally, what you need to do is you need to give it, I would say, hundreds or thousands, and actually literally tens and thousands of such articles, so that it can, start to make meaning out of, these sentences and what these articles are saying and so on. Okay, so we're almost there. Let's just wait for a few more seconds and then we should be done with training our small LSTM neural network. Okay, there you go. So we have trained it. Our loss is not gone all the way down to 0, but it is low enough. It started at 6 something. It's gone down to 0.0853, which means that it has learned something. Actually, let's do this. I'll do LSTM dot summary to see what is my network size. Okay. So if you can see, this network has about 2.2 million parameters of which 744 of them are trainable parameters. Okay. So it's a very small network in the context of language models. This is considered to be a very, very small, tiny model, which is fine because our goal is not to go and train it across all the articles on the internet, but just to get an understanding of how LSTM is used. Now, before we start to use this train model to start predicting sentences, let's just go and do a quick recap of what we have seen so far in terms of how the LSTM is built. You have your embedding layer attached to that an LSTM layer. So it's basically a few characters, one line of code, and you can essentially build an LSTM model, okay, using the TensorFlow Keras library. Okay, now that our model is trained, let's complete the sentence. So what I'm doing here is I'm going to give it a prompt. Let's say I just give it one word. We'll give more words shortly, but let's say I give it one word, Modi, who's the Prime Minister of India. Clearly, because this is article is about Modi's visit to United States. Okay, so I want to see how it completes the sentence if I just give it one word called Modi, and I would like it to complete the sentences by adding 20 more words that come after Modi. Okay, and the way it is done is basically you start with tokenizing your seed text. Seed text is the prompt here, and then you basically go after the total number of tokens you'd like to predict, which is 20 here. You would do the same thing. You would pad the sequence with maximum sentence length. Then you will pass it to the prediction model.predict. Model is basically the LSTM model that we built. Then it predicts the next word. We will use our vocabulary to convert the token ID into the actual word and then print that word. Then we go and add that word to our the seed text to our sequence, because Modi, and let's say it predicted another word. You add that word, then you pass it back. It predicts another word, then you add that back. So this is called an auto-regressive mode of generating text. Okay. Again, I explained this in previous episodes. I'll not go into more explanation here. But now let's go and run this. So I'm giving it one prompt word Modi, and then expecting it to generate the next 20 words. Okay. So it says Modi looks forward to hosting President Trump in New Delhi for Quad Leaders Summit, ahead of which the leaders will. I think this is a very good prediction built on top of a very small LSTM network. Okay, let's say I want to change this to Trump. Fine. Let's copy this and then run it here. Just change it directly. Let's give it this. Let's say Trump. What does it predict now? Trump and Prime Minister Modi noted the importance of advancing the people to people ties between the two countries. I mean, for such a small training sample set and a small network, I think it's doing a pretty darn good job of predicting the right sentences. Let's say I do one more thing. Let me create something that's more than, I'll give it a longer prompt. I'll say, what did Trump and Modi agree on? Let's see what it says. What did Trump? This India roadmap for defense industrial cooperation and recognizing the rising importance of autonomous systems, and the leaders announced. So obviously it's not putting sentence markers like periods and all that stuff, because the way you do that is that you actually train the neural network into showing where a sentence ends and all that. We are not doing that, so that's fine. But I think it's again done a very good job. So as you can see, our small LSTM network is doing a pretty good job of completing sentences. Now, obviously, if you train it on many more articles and give it more training time and all that, and build maybe even a larger network, he'll start to make more accurate predictions. But I think it's pretty impressive, even what our small toy LSTM network has done so far. So it's time now to wrap up this episode. Let's do a quick summary of what we have studied so far. A LSTM, which is an optimization on top of a recurrent neural network, introduces this concept of short-term memory as well as long-term memory. Short-term memory exists in an RNN. An LSTM adds long-term memory to that. And it has this concept of a forget gate, an input gate, an output gate. And using these two, it is able to get across the limitation of an RNN where it does not understand longer sequences, and LSTM can because of this additive property of the long-term memory. All right. With that, thank you very much. And if you like this content, please subscribe, like, and share this content with others. Thank you and happy learning.